All right, this video is going to talk about graphing exponential functions. It is 2 sections of a textbook that I want to do in under 15 minutes for sure. So we are going to get going right here. So the best way to think about exponential growth is to actually contrast it with linear growth. Linear growth, you would start at 0, 0 for this equation here, and then rise up 2 for every 1x. You can see you just add 2 each time. However, this function right here says, hey, for your next one, don't just add 2, actually double it. So multiply by 2 each and every time. So you're going to have the same percentage increase over time versus the same amount increase over time. So that's why when you have exponential growth, you actually grow really, really quickly, is you're growing that same percentage increase over time versus just adding in a certain amount. There's a general form to an exponential equation. It's going to be a in the front times b to the x power. If you have a base b raised to the x power that is greater than 1, then you are going to grow fast. You are going to have a growth rate function. However, if you have a b value that is between 0 and 1, then you are actually going to have an opposite situation where you have decay or exponential decay, where maybe you like have half of something instead of twice of it. You can see that there's a table of values here and a graph of what exponential looks like. And so let's look at how to make a graph if you maybe have 2 data points and know that we have an exponential function. So if there were 80 deer in 2006, and then by 2012, we knew that the population had grown to 180, then we want to find an exponential function here. Well, I'm just going to let 2006 be times 0. Oh, this says to use n. All right, so then 2012, 7, 8, 9, 10, 11, 12 would be year 6. And it's up to 180. And it says I know that this grows exponentially, so I know my graph looks like this, but I want to find the actual equation. Well, I know that n of t must follow this formula, a times some base to the power of t. Well, I know that that's 80 when time is 0. Using exponential properties, anything to the power of 0 is 1, so a must be 80. So my n of t equation must be that initial value times b to the power of t. Next, I know that 180 is equal to 80 times b to the power of 6. I'm going to divide 180 by 80, and I get 2.25 equals b to the power of 6. And to undo that power of 6, I'm going to take the 6th root of that number. And so base is approximately 1.145. And so my final equation would be that n of t is equal to 80 times 1.145 to the power of t. Notice 80 is not raised to the power of t. That is my power of t. Now, I want to make sure that we understand the pieces that are at play here. That means that I would have a function that grows exponentially instead of decays. I know that. And my proportion of growth is going to be 1 plus whatever my growth rate is. So that means my growth rate must be about 14.5%. Okay? Because if you have your deer, they already stay there, right? Pretend like that's a deer. Okay? whenever you have that and then you're multiplying by that percent, like we have that increase, right? But then you have to add to the original amount of the deer. So whenever you have that plus 1, that piece must be your percent increase. We can talk more about that in class if you need some more clarification. All right, what if I have these 2 points here? So if I know that y is equal to a times b to the x, and I know that 6 equals a times b to the negative 2, or 6 equals a over b squared. And I know that 2 equals a times b to the power of 1. Maybe I solve this for a by saying like 2 over b equals a. Well, now I have 2 equations and 2 unknowns. Maybe let's solve this for a as well. So I'm going to move b squared over here by multiplying. So I have that this is equal to a and this is equal to a. Well, that means that 6b squared must be equal to 2 over b. If I multiply by b, I get b cubed. And if I divide by 6, I get 1/3. And so b must be the cube root of 1/3, which gets me 0.693. And then I know that 2 over b gives me a. So a must be 2.885. So my equation up here must be 2.885 times my base to the power of x. Now in this equation, it should see that then I would have exponential decay because I have a number here, my base is less than 1. And so if I think about what my exponential decay is, it would be 1 minus whatever the percent of decay is, would then get me this right here. So my percent decay would be like 30%-ish. All right, here are some graphs just so you can see it. Again, if b is bigger than 1, we're going to have exponential growth. If b is between 0 and 1, we're going to have exponential decay. We don't worry about having negative numbers for our bases for exponentials. And then let's talk about how to do some transformations. So this is going to be the graph of y equals 2 to the x. But notice my plus 1 is inside with my x value inside my function piece. So this is going to be moved to the left 1. And then my minus 3 is on the outside, so it's going to be moved down 3. So my original function is going to go through at 0, 1. That is one common place for all exponential functions is x equals 0, y equals 1. Notice I have this horizontal asymptote on the left-hand side. So I'm going to keep that by moving it down 3. And then I'm just going to move this point left 1 and then down 1, 2, 3 as well. And then draw in my new graph like so. Now stretches and compressions are going to be only done through A. One thing I want us to also look at in this case is when you do have a base that is between 0 and 1, that we can rewrite this as well. So if I had 1/2 to the power of x, another way to write that is 1 to the x over 2 to the x. Well, 1 to the x is always 1. And so I could write this as 2 to the negative x power. Therefore, f of x in this case is 4 times 2 to the negative x. So that's another reason why I'm going to be able to think about 0 to be as exponential decay, because this says to flip the graph y equals 2x over the y-axis. This piece here then says stretch it by a power of 4. So that would be our graph of our function right here.